So hello everybody.
Hello.
Okay.
Hello.
Yeah.
Hello.
So
Hello.
yeah. So now we will try to. Okay. I have something strange here. Okay. So now we have an example. We need to test this example. Maybe you can go to the slides one more time before doing this. So we have here very simple example. We just need to load and visualize this iris dataset. So as you can see here. Yes. So first we need to load some. We need to use some. I mean those libraries, for example. So we need to import it. This is the interface. So we need to import num_b as nb, for example. This is very important for maybe some mathematical calculations if we have. I guess here we don't need to have it in fact, but I'm just copy and paste it each time. So num_b as nb, matplot lib.py pyplot as plt, for example. This one is used for plotting. So this one is very important for plotting. There are some other libraries which can be used for plotting also. This one, for example, SNS, you can use it for plotting. And pandas, for example, pandas, you need it. Pandas, in fact, you need it. In fact, if you are working with Excel files, maybe I don't need all this here, but I just. But this one is very important if you are working with Excel file which has data. I will give you an example today, hopefully. Where we have an Excel file and we need to load data from this Excel file, maybe plot it, try to use some statistical tools to get some, better understanding of it, for example. So in your paper, for example, you should have a part about the data, visualize the data, statistical description. You can just generate a table in your that section. It will be statistical description of the data, for example, and so on. It will be very, very nice to say something about your data. And after that, you can follow it by data pre-processing section, if we will normalize, standardize, and so on. So it would be nice if you can have something about your data in your code. And after that, I imported data sets from sklearn because I need to get iris, and it's easy to get iris from sklearn.datasets. So iris equal datasets.load iris. And as I told you, you will have all data here. In iris here, it will have X and Y. It will have the data, and it will have the target values. So those data, in fact, it's features, and the target, it's Y. It is the output. So if you want to print those feature names, what will be the feature names and the target names? Target names, it's this one, in fact. No, this not this one. So target names, it's Setosa. Versicolor, we have three classes. One called Setosa, one called Versicolor, one called Virginica, right? So we have three classes. And after that, you can use a scatter plot, for example. So I need to plot, because when we loading the data here, I got the first two columns. Do you see this one? This one means we got only the two first column, which is Sybil length and Sybil width. So we have the input will be 4 column, right? So the first column, this is column number 1, column number 2, 3, and 4. So here in my part here, I try to load only the first two columns because I want to plot it in two-dimensional space. So I will use a scatter plot. The first input will be Sybil length, right? And the second input will be this Sybil width, right? And after that, I will just C equal Y, class equal Y. I have here Y. This is my target. So C equal Y, it means we will color it. We will color it according to we will give it different colors according to the labels which we have. And because we have three classes here, we have Setosa, we have Versicolor, we have Virginica. So some of those points are coming from for class Setosa, some for Versicolor, some for Virginica. In fact, in this iris dataset, it consists of 150 data points. 150 data points. The first 50, it's for one class, and the third 50, and the third 50. So this is a third class. So we have three classes here. So if we can just replace it by zeros and ones, maybe this one will be zeros, 0, 0, 0. This one will be ones. This one will be maybe 2, 2, 2, 2, and so on. So we have three classes. The first class will be Setosa. This one, it's Setosa. This one, it will be Versicolor. This one will be Virginica, right? So when we are plotting it, I'm plotting the first two column 1 and 2, for example. So Sybil length, this one is Sybil length and width. So we will have Sybil length and Sybil width, and we will color it with according to different, we will give it a color according to the different class or different label, for example. So it will be like this. So scatter plot is beautiful because it will just help you to visualize your data. So also, if you are working, in fact, with any type of data, if you can plot it, it will be beautiful, right? So in your paper, you can have a section about data set, for example, and you can just say something about the data, how the data was collected, how many data points you have, how many input features, how many target features, right? How many classes. A statistical description, you can have a section called statistical description where you can get a table describing your data, for example. And if you can plot it, it will be beautiful. It will be nice. And after that, you will go to section 2, which is data pre-processing, right? If you look into our data here, you can see that we have very nice class, which is Setosa. This is one class which called Setosa, right? And after that, we have other two classes, versicolor and virginica. They are mixed together, in fact. A huge overlap between those two classes. So you can, if you can look into it, we have like, maybe this is one class and another class. Maybe another one here, like, right? So this is class class 0, this is class 1, this is class 2, for example. And you can see for class 0, it's perfect. I can just draw a line. So if we want to classify it, I can just draw a line like this one. All data points above this line will be classified as Setosa. All data points below it, it will be classified as versicolor and virginica. So this one will be my model, in fact. This one can be my model. But as you can see here, this model, it performs well with Setosa, but it performs very bad with the other two because other two are mixed. It's complex, right? So the other two classes are mixed because maybe they are close. I mean, Sybil length and width, they are mixed. But it's clear, in fact, for the Setosa, when Sybil length increases and the Sybil length decreases, or maybe the Sybil width is very high compared to the Sybil length, it will be Setosa. So it's easy to, so maybe for experienced people, it will be easy to just classify it into Setosa and maybe the other two people will be confused, right? So for versicolor and virginica, maybe some people will be confused. It's not easy, in fact. It's not easy using those two features. So using Sybil width and Sybil length, it might not be sufficient to correctly classify the three classes because now we are using only two classes, right? We are using, sorry, two input features, right? So two input features, it does not carry enough information to classify correctly the whole data set. But I can see it from Sybil width and length that it should be possible to classify Setosa with 100%. It's very clear that Setosa is very far away from the other two groups. The other two groups are overlapped, and it will make some confusion. So in this case, we need more additional information to classify it. So if you can go to, okay, I will go to the link, and we will try to we will try to run it in Google Colab. Yes. I don't know. Oh, sorry, not this one. So I will just open my file in Google Colab. Can you see my screen?
Yes.
Yes.
Yeah, this is very good. So if you want to open new file, just from file, new notebook, you can open a file. If you want to open something which has been done before, just to open notebook, you can upload notebook, for example. So you can write something in Jupyter notebook and upload it here or download it and so on. So it should be possible. And of course, you can save it to GitHub. You can save it in a drive, for example. And of course, you can share it, right? So here you can just share. So when you are writing your Google Colab, you can share it with other people, for example. If you and the other people are working together in the same problem, you can share the code together so people can help each other. We have here also tools setting. For example, runtime, you can run all. correct? Or run selections. You can just go here for each block and just run it, for example. Correct? So you can run it one by one, for example, and so on. And runtime also, you can change runtime type. So here, when you select runtime type, you can select CPU, for example, T4 GPU, for example. Changing runtime attributes may terminate your current session. If you will do it, you need to run your code from again, for example. So you can just say save, okay, and you need to run it one more time. So it will be just run all. It will run the two blocks which we have. So as you can see here, as you can see here, okay, because it has other part here. Yeah, sorry. So here you can see here, iris feature names. Feature names, we have sepal length, sepal width in centimeters, petal length, and petal width in centimeter. Target names, it will be Setosa, versicolor, virginica. And as you can see here, when we are plotting it, it's clear that Setosa is okay, is very good, in a very good location. Because maybe here, when you look into this figure, you can see that for Setosa, sepal length is much less and sepal width is high, is large. So this one is okay. So there is big difference, big distance between this cluster and those other two clusters, which is versicolor and virginica, which means it's difficult, in fact, for versicolor and virginica, it's mixed. There's too much overlap, so it's challenging, in fact, to classify versicolor and virginica because there are too much overlap between them. So it's challenging. But for Setosa, it's easy. I can just use a linear model. And if we need to get this linear model, we just need to draw a line. Linear model means it's line. So I can just draw a line. And no, I cannot draw here. So I can just draw a line, and this line will be my model. And it's easy to get a line. Line, in fact, we can generate a line from a perceptron, right? So in fact, you can do lots of stuff here. You can also try to use pre-processing. So you can see here pre-processing from sklearn. I can run it. Label, oh no, it's not working, maybe. Yes. So please, maybe you can have 1 minute to go to this link and try to maybe test other features. So for example, I can change maybe feature 2 and 3, for example. So if we want to change it, so I'm selecting here, I mean x0 and x1, for example, or x1 and first two features. For example, I will select two different features, for example, and try to see how it will look like, right? Yeah, so I can select, for example, maybe 2 and 3, right? So in this case, we will use petal length and petal width, and we will run it. Do you see? So Setosa also, it's far, but now, in fact, it's much easier. In fact, if you can see it here in front of me, it's much easier, in fact, to classify versicolor and virginica. So in fact, petal length and petal width are much better than sepal length and sepal width for my classification problem. Do you see? When we are using petal length and petal width, there is little overlap between the two classes, but it's very little, right? So we will be confused here. Maybe we will have some few examples where it can be classified both versicolor and virginica. So those input features are very important, very, very important. So is it okay to take maybe 2 minutes and for you to look into this link and try to test it by yourself?
Yeah.
Okay. When you finish, just let me know, please. In fact, we can try to get some.
We're just supposed to play around with the plotting, right?
Yes.
Yeah.
So, can you plot
on that
it?
list? Yeah.
Okay,
Yes,
very good.
it's no problem.
Yeah, very good. Okay, so in this case, we can go to the next slide. Yes. So the second example here, it's a very simple one, where we try to use Panda for reading Excel file. So this is, I mean, when we are working with data set, which we import from sklearn, for example, or Keras, it's very easy to deal with because it is already, in fact, sometimes also it's maybe scaled, standardized, divided also into training set and testing set, for example. So usually they prepare it for you, so you can just download it and work with it. But sometimes you have your own data in a CSV file, for example. So in this case, you need to learn how to use Panda, for example, pandas, for example. So you can import it and try to read this CSV file, for example, or Excel file, and try to display it and try to plot it and so on. So as you can see here, in this case, your data file, it's in CSV file, and so in this case, we will just download a file, and after that, maybe if you want to use oh my God, yes, if you want to use maybe Google Drive, you can upload it to Google Drive, and you can just load it directly to your Google Colab, for example. If you want to get access to Google Drive, you need to mount a drive using this command. And after that, you will use Panda. And Panda, it will help you to read your Excel file. So I will just read the Excel file and I will save the contents in Iris. So you can plot it using iris.head because it's a data frame, right? In a form of a data frame. So you can just use this command for plotting the first 5 lines, or maybe using a tail also for plotting the last 5 lines or something. And once you have your data set, now we load our data, and you can see that we have four features. We have sepal length, sepal width, petal length, and width. So we have 4 features as we did before. And the column number 5, this one will be the target features. This one will be the target features. Target features or labels or classes. This is my labels. So you can see it's a Setosa, Virginica, versicolor. So if I need to train a model, in fact, I cannot use the text here. I need to replace it with numerical value. So for example, I can replace Setosa with zeros, maybe Virginica, for example, with 1, versicolor with 2, and so on. So I need to replace it with, because it's categorical variables, and I cannot deal with it as it is now. So maybe you can use a command. We can import pre-processing from sklearn, and it's called the function called the label encoder. In fact, you can do it. You don't need to do this approach. This approach is very quick, but of course you can just replace, right? I can replace Setosa with 0. It's easy in data frame. When your data is a data frame, it's easy. So you can just replace all Setosa with 0, all Vergy color with 1, and so on. But you can use also this command from pre-processing from sklearn, and it's called the pre-processing.label encoder. So you need to define this label encoder object. You will have this label encoder, and after that label encoder.fit transform. It will transform the data, and you need to specify which column. So it's iris of variety. This variety, it's the column, the target feature. So I need to encode this one, right? This column. So I need to do that part here. So in this case, it will do this process quickly, and it will replace it with, in order. So we will use Setosa will be replaced by 0, Virginica it will be replaced by 1, and versicolor it will be replaced by 2. So now it's numerical values. So now I have the sepal length as a number, sepal width is a number, petal length, petal width. In fact, when we are working with a data file from Excel sheet, we need to check that we have all data points. Maybe you have some missing values. Maybe in the sepal length, maybe in for some records or some examples, we don't have this number. It's missing. If it is missing, in fact, we need to replace it with a number also. So the idea here, if you have many missing values in a row, you can just delete the whole row. So imagine that you have one row here, and you have, for example, 3 missing values of 4. So we have only this one. So in fact, it doesn't need, you don't need to keep this whole line because you have lots of missing values. So you can just delete the whole row. You don't need to keep it. But if you have one missing value or 2, for example, so in this case, we can replace each missing value maybe by the average, correct? So I can take the average of the whole column and I can replace the missing value here with the average, for example. So also, in fact, if you can, so it's bear plot. So we have something like maybe correlation or something, or bear plot. Maybe there is a function called the bear plot, which can plot all those variables against each other, for example. So I'm plotting here a sepal length, maybe against the target features, against those variety, for example, the target features. So I have 3 classes. So what will be the impact of the sepal length on those? So it carries information which can be used for classifying each class, right? So it's like correlation coefficient or something. So in fact, there are many ways to visualize and try to calculate the correlation coefficient between the features. So okay, so it's just the tips for if we need to run our model locally or on the cloud, because some people they try to run their models on the cloud. So in fact, build, train, and deploy machine learning models quickly requires massive computational resources. In fact, we have cloud provided by NTNU, which we can use. It's Edon. It's called Edon, right? So you can get access. You search for it, contact the people, and they can maybe make an account for you, so you can get access to it, for example. So you will need fast enough GPU to do deep learning experiments, especially if you are working with a large data set and a large model. So maybe the training process to train the model for one epoch, it takes 30 minutes, for example. So in this case, you need a really huge amount of time. So in this case, it would be smart to get access to some GPUs. Maybe you can have a GPU online locally in your computer, or maybe you can just go to the cloud and try to run your model on the cloud. And in this case, I guess you need to upload your data and your model on the cloud. So it's when you're uploading it to a cloud, for example, it could be commercial cloud like Google Cloud, Amazon Web Services, IBM, and so on. So in this case, maybe it's challenging because maybe you are working with confidential data and you don't want to share the data with a third party. So in this case, you need to avoid those solutions. And maybe you need to go to Odin Cloud, which is provided by NTNU because it's more safe, right? It's more safe. So you have this Edon HPC cluster. HPC, it's high performance computing. So you can contact the people there. There is the link, in fact. This is not the link, but we did last year. In fact, I asked one of my students to prepare like user manual for people to know how to use this Odin HPC cluster, because many people were not able to use it, especially in person, because we are not able to attend those. They provide, in fact, some training in Trondheim, but not in Olosond. So if you want to attend, you need to travel. So it was difficult. So we prepared this user manual last year for people to know how to get access to this Odin HPC cluster and to use it, how to use it with some examples. So you can go to this link and you can download this user manual, and it will help you to know how to do this process. And it's more safe. So it's much better than I mean, running your model in a commercial cloud, because if you are working with medical data or something, maybe it's not allowed to share your data on a cloud. So it's better to go for maybe a local solution, run it on your GPU, or try to get access to Odin cloud, because it's much safe. So at the end, course assessment, as we mentioned at the beginning, is it's portfolio assessment, where sample of the work will be used to evaluate intended learning outcomes. But as I told you, we can make this one small assignments, but it's much better to combine those small assignments into one large assignment. It would be this conference paper. And this conference paper, it would be useful, so you can get it published and you can get some credits from it after the course. It could be something in your PhD, so try to focus on it. Try to write high quality, at least a conference paper. So it could be also part from your PhD thesis. It would be very, very good. And after that, you can expand it to a journal paper if you want. So if you write a conference paper now, maybe later on you can try to expand it and extend it into a journal paper. Grading, it's pass and fail. And in fact, to pass, you need to get more than 70%. It's not 50% or something. So we don't have here E and D, and it's pass and fail, but pass is high pass. So it's like B. You need to get B in order to pass a course. So you need to write very good report. And as I told you, it's 6 pages. And if you a conference paper, for example, and a conference paper, it consists of parts, you need to fill in those parts. You need to write high quality text. And in the machine learning part, you need to say something about the data set, data collection, data pre-processing, model selection, the training process, validation protocol, and you need to communicate the performance of your model in the best way, in the right way. So it's not a big deal. I mean, to write 6 pages or 8 pages, it's nothing. In fact, it should be something very, very simple. And if you can start from today, create a template and start working. When you have some free time, try to write something. And just remember, you will use this paper for passing the course, and at the same time, also it will be a publication in your publication list. So it will be something very nice. And you can work with other people, but if you will work with other people, try to make something which is high quality, please. So we should expect the quality will be much higher when we have a team work. Yes. Okay, thank you very much. This is the first part, and after that we will go to the second part. Maybe we can take also maybe another 10 minutes or 15 minutes and take a break so people don't get tired. So, types of machine learning. We need to talk about different types of machine learning models. It's quickly, there are 4 branches of machine learning. We have supervised learning, and in this course we can work in supervised and unsupervised, in fact. So supervised learning, this is by far the most common case, because when you are working with the data, you want to build a machine learning model or AI model which can perform at the same level of human intelligence, for example. So I need to train a model, and to train the model, you need something called teaching signal or target signal. This target signal, it will be the one which will be used to quantify the performance of your model during the training process. So we will use this target signal or teaching signal to calculate the loss, and the optimizer will try to adjust the model weights or parameters in a way to minimize this loss. So if you want to minimize loss, I need to calculate loss. To calculate the loss, it will be the difference between my target features, my actual classes, and my predicted classes. So I need to compare the performance of the model. So I will subtract all time the actual real classes from the actual classes from the predicted ones, and we will calculate loss value, and the optimizer will try to adjust the weights of the model or the model parameters in a way which will minimize this loss function. So this is supervised learning. So supervised learning, it's easy to understand, and it's a most simple case, most common case, and we will use it in this most of the machine learning, examples which we will use in this course, it will be supervised learning. Unsupervised, on the other side, it's a branch of machine learning which consists of finding interesting transformation of input data without the help of any targets. We don't have any targets, right? For the purpose of data visualization, we can use it for data visualization, data compression, data denoising, for example, or to better understand the correlations present in the data at hand. So we use it. Of course, there are models which can be trained in unsupervised learning. Some models, we will talk about it, but also it is used mainly for data visualization, data compression, denoising, and so on. So for example, imagine that you have a data and it's a large, the dimension is very large. Input dimension is high, for example. So I have 20 column, for example, 20 input features. So I cannot, it's too much for my model. So if I will use 20 inputs, maybe it's too much. And so I can compress it. So I can convert it from 20 to 10 or to 5. So in this case, maybe I can use principal component analysis. And the principal component analysis, it's an unsupervised technique, in fact. It's unsupervised. And the principal component analysis will try to convert the data from its original dimension into a reduced dimension. So I can convert it from 10 to 3. And then when it is 3-dimension, in this case, in fact, I can visualize it in 3-dimensional space. Or I can convert it in 2-dimensional space and visualize it. So it is used, in fact, it helps us to visualize complex data by compressing the data. I can need to compress it from high-dimensional space into a lower-dimensional space. Data denoising also, we can use also some models for the denoising, and it's unsupervised. I will provide the input to the model, and it will try to remove noise. So I don't have any target feature, right? We don't have any target. So for example, we can use autoencoder for denoising, for example. The autoencoder, it's a feed-forward neural network, but it is trained in a supervised way because we don't have any target, we don't classify. So the input will be an image and the output will be an image. It's the same image, in fact, correct? And I can use it I can train this autoencoder for dimensionality reduction. I can use it to lower the dimension or feature selection, correct? Or I can use it for denoising. If I want to use it for denoising, it means the input will be the image with the noise, and the output should be the image without noise. And I will train the model using input images. We don't have any target. So in this case, I can train the autoencoder to remove noise from input images. So just remember, the autoencoder, the input will be an image, the output will be the same image. And I can use the same image, exactly the same, and I can train this autoencoder for dimensionality reduction. I need to reduce the dimension of the input from, for example, 28 times 28 to something less, or I can use it as a denoising for denoising. When it is for denoising, in this case, I need to just make a small trick. The input will be the image plus noise, and the output will be the image without noise. So in this case, I will train the autoencoder to remove noise from images, right? Unsupervised learning also is the bread and butter of data analytics, and it is often a necessary step in better understanding data sets. It's important to understand the data using unsupervised learning. Dimensionality reduction and the clustering are well-known categories of unsupervised learning. So dimensionality reduction is very important. When you are working with a high-dimensional data set, you can try to reduce the dimension using autoencoder, and the autoencoder is unsupervised learning, can be trained in a supervised learning approach. Clustering also, clustering techniques, it's unsupervised because we cluster the data based on the inputs, not based on the outputs. I don't have any targets. I don't have any clusters, any classes, but I will cluster it based on the input features. And I have very nice example for clustering. For example, coins. You have a set of coins in your hand, for example, and you try to, without looking into it, you try to classify it or cluster it. So for example, you have in your hand maybe 20 krona, 10 krona, and 5 krona, 1 krona. I guess in your hand you can cluster it without, even just to close your eyes and try to cluster it, you will cluster it correctly. How this happened, in fact, by just touching it. and try to feel how heavy it is. So maybe heavy coins will be the 20. The other one will be 10. The other one will be maybe 5 and 1. So just by the size also, radius, correct? So you can just touch it and feel the weight and feel also the radius of each coin. So now, in fact, weight and radius are input features. You didn't look into it. Because when you look into it, you can just cluster it. You can classify it. This one 10, this one 20, this one 1 krona, this one 5 krona. It's easy, correct? But if you want to test this unsupervised learning, for example, just touch it without looking into it and try to cluster it according to some features. Those features could be the radius and it could be also weight. So I have 2 features. And based on those features, I will cluster my dataset. My dataset here will be coins. So I can cluster it according to the weight and the radius of each coin, individual coin. And he will do it. So this is unsupervised learning. We don't have any target signal. We don't have any label, right? So just to try to do it, you will be able to achieve it. So this is dimensionality reduction, which is important, and also there is something called self-supervised learning, and the self-supervised learning is supervised learning without human annotated labels, right? It's supervised, but we don't have annotated labels. You can think of it as supervised learning without any humans in the loop. So there are still labels involved, but they are generated from the input data, typically using some heuristic algorithm. So self-supervised, we need to have some algorithm which will be able to give us some labels. We don't have labels, we don't have any humans, but we will have some heuristics which will help us to label, annotate my data. So predicting, for example, the next frame in a video, given best frames, or the next word in a text given previous words. On the other side, there is something called reinforcement learning, and reinforcement learning is exciting area, in fact. So in reinforcement learning, we have an agent, we call it intelligent agent, and this intelligent agent, it could be a robot, in fact. It will receive information about its environment, and it will try to learn how to choose actions that will maximize some reward. So imagine that you have an autonomous car, right? And it has autonomous driving, for example. You're sitting in your car, you told your car, please, I want to go from here, school, to the home, correct? So it will try to sense the environment. And in this car, it has sensors around it, and it has access also to maybe Google Maps. So maybe one road was closed, right? So it will not take you from that road, in fact. It will not be smart. Maybe this road is closed or it's crowded because you want to reach home quickly. So in this case, it will select a different way, which will help you to achieve this reward function. This reward, I need to reach home early, quickly, right? So it will select actions which will try to achieve this cost function or objective function, for example, or reward function. So it will select the actions which will help you to achieve this goal. It could be also a neural network which looks at a video game, for example, and try to output game actions in order to maximize its score. It can be trained also using reinforcement learning. So I can have also a game. So instead of pressing keys by yourself, you can just have a neural network which will analyze the image, and it will try to select actions which will maximize your reward function. So in supervised learning, we learn from data. We are learning from data. So data is very important. In supervised learning, we are learning from data. And also in unsupervised, also are learning from data, in fact. But we don't have labels. But in reinforcement learning, we are learning from our mistakes. Because this intelligent agent, it will do some mistakes. And when it will do a mistake, it will get a negative reward, -1, for example. And it when the action is correct, it will get +1. So it's according to the reward function. It will try to avoid actions which will minimize your reward function, and it will try to select actions which will maximize your reward function. Yes. So now we are talking, we talk about types of machine learning. Now we need to talk about machine learning problems, right? So we know that learning, there is supervised learning, unsupervised learning, maybe self-supervised or something, and reinforcement learning. But what about the problem itself? So the problem itself, we have binary classification. So the binary classification problem, we have 2 choices, right? In binary classification problems, we have only two outcomes in binary classifications. So it's a supervised learning. Since the training data set is labeled, we have labels. It's binary classification, so we have classes. So in this case, we have labels. And when you have labels, it means this problem, it's a supervised learning. Classification task where each input sample has only two classes or two outcomes. It could be 0 and 1, no and yes, for example. So examples, it could be medical diagnosis. Someone has COVID, someone does not have COVID. So it's a binary classification problem. Spam detection. This email is a spam or ham, for example. It's a binary classification problem. Credit card fraud detection, right? So it's a binary classification problem. And so on. Iris dataset. In Iris dataset, which we just saw and draw, it has three classes. When it has three classes, it's not binary classification problem, it's a multi-class classification problem. Because we don't have two outcomes, we have three outcomes. So binary classification problems, it has only two outcomes. And the decision should be yes and no, and so on. In multi-class classification task where each input sample should be categorized into more than two categories or classes. An example could be classify a set of images of fruits, which may be orange, apples, pears. So I have an image, and this image has maybe more than two, because if it is orange, it's orange or not, or orange or apple. But if we have more objects, so in this case, it will be multi-class classification. Also, classifying handwritten digits. Handwritten digits, we have famous dataset called the MNIST dataset. So this MNIST dataset, it's a dataset of handwritten digits, and those handwritten digits, it's digits from 0 to 9. So in fact, we have here 10 classes. So it's multi-class classification. Iris dataset. In Iris, we have three classes, right? So we have 0, 1, and 2. So in this case, we have three classes. So it's a multi-class classification problem. Most of the problems which we will work with, it will be multi-class classification problem. Also, there is another problem, which is multi-label classification. It's not multi-class, but it's multi-label, which means the classification task here, where each input sample can be assigned multiple labels. For instance, a given image may contain both a cat and a dog, and it should be annotated both with the cat label and the dog label. Number of labels per image is usually variable. Maybe you have some object which can be classified into two labels or more than two labels at the same time, right? So in this case, it will be multi-label classification. It could be annotated, it could be classified into dog, and at the same time, it could be classified into cat, for example. Scalar regression, regression problems. We know regression problems. So the task here is the target is continuous scalar, right? For example, predicting house prices. So when you are predicting house prices, it's not yes and no, it's not a class, but it's a continuous scalar. It's a number. Predicting wages, income, right? So it's also continuous number. So I need to predict your income next year, for example. So it should be number from this to that with a range. So it's continuous scalar. So in this case, it would be regression problems. For our machine learning problem, in fact, the difference between classification and regression, in fact, we regress. I mean, even all classification problem are regression problem. And after that, we will convert this regression problem into a classification problem by selecting an appropriate activation function. So in fact, I mean, the machine learning, it knows nothing. In fact, it does not know classification, but we change it into classification. It regresses, in fact. It calculates continuous number. And after that, when we calculate this continuous number, we can say that, imagine that it's a binary classification problem. So the output, we try to predict the output. So the output will be a number between 0 and 1. We can say that when it is 0.5 and more, greater than 0.5, greater than or equal, it will be classified as dog. Otherwise, it will be classified as cat. So in fact, each classification problem is a regression problem in reality. Each classification problem, it's a regression problem. But I mean, after solving it, we need to convert it into something which we can understand. So we will calculate a number. This number, it could be probability, right? So the output here, it could be probability number. This number, it is a number between 0 and 1, right? It could be a number between 0 and 1. We can just say that we can draw a line here, and we can say that all probabilities above 0.5 will be classified into a dog. Otherwise, it will be classified into a cat, right? So So in reality, all classification problems are regression problems, but we try to modify it in a way to give us decisions, a clear decision, yes and no. Because in some problems we just need to get yes and no, right? Or class label, dog or cat. So we need to convert it to something which we can understand it. But in reality, in all classification problems, we calculate probability because if you have an image and this image it has a dog and a cat, for example, I want to classify it into the dog and the cat. So I calculate the probability. So what will be the probability that this object or this animal is a dog? It could be 0.6 or 0.4, right? When it is 0.4, it means it's not a dog, it's a cat. When it is above 0.5, it could be 0.8, 0.9, 0.7. So in this case, when it is above 0.5, we can say that now this is a dog. If you go to another country, for example, where dogs are very small, right? So maybe in this case, your model will be confused and it will classify many dogs as cats. In this case, you need to change the threshold value, right? So the models which are working here, it's not working in some other places, right? So we need to make some changes to your threshold value to convert your regression problem into a classification problem by selecting different, maybe changing or modifying your threshold value. Yes, model development. I mean, later on we will work with, in fact, we will work with this pipelining in machine learning. It's very important and it's very professional when you are working with the pipelining. But here we will just talk about model development process. So the model development process, it consists of some steps which we need to follow. So first, you need to define your problem. It's very, very important to define your problem. So even if you are writing a research proposal, you need to define your problem. You need to define some research questions. And after that, based on those defined research questions, you will propose a solution. And based on this, you will start collecting data. So imagine that you have a research question and you said, okay, we will answer this research question using machine learning. But machine learning, it's data-driven. When it is data-driven, it means we need to collect data. So we will start collecting data. And after that, I need to train my model. So I need to select a loss function or an accuracy or loss value, prediction error or prediction accuracy. So we need to choose a measure of success. This measure of success, it will be your loss function. This is the loss function which will be used to evaluate the performance of my model. So I need to select this loss function. It could be mean square error, mean absolute error, right? So you need to select this loss function. And after that, you will define an evaluation protocol. I will validate my model using maybe cross-validation, correct? It could be cross-validation or it could be hold-out validation. So you need to decide what will be your evaluation protocol or to validate your model, validation protocol. You will prepare your data for training. What do you mean by preparing? Maybe I have some missing values. If I will feed these numbers to my model, I will get an error message because my model cannot deal with no value. It cannot deal also with categorical variables. It cannot deal with cats and dogs. I need to convert each dog into 1 and each cat into a 0. So I need to prepare my data. I need to maybe normalize and standardize my data, because if it is normalized and standardized, maybe the model will how do you call it? It will be difficult for my model, right? My model will suffer a lot. I mean, to train, to converge. So it will be nice if we can normalize and standardize our data. And after that, maybe develop a benchmark or a baseline model. It's smart, in fact, at the beginning, to build a baseline model. This baseline model, it just has accuracy equivalent to maybe like tossing a coin, 50% accuracy, for example. And after that, you will try to enhance the performance of your model. So it's much better to start with a baseline model, basic model, simple model, which just can classify with accuracy close to 50%, 60%. And after that, he will try to make it complex step by step to enhance the performance of your model. Don't go into the opposite direction. So some people they have a data and they can just select a very complex model from the beginning. Maybe this model will overfit your data, and maybe you will not discover that the model is overfitting. So it will be a problem. And it's a problem, in fact, to solve overfitting problem. right? Because the model overfits my data because my data set is small. Maybe the model is too complex. So in fact, it's much better to start with a baseline model, and after that, you try to increase model complexity step by step to enhance your performance. So it's much better to start with a baseline model rather than starting with a complex model. After that, develop a better model. From this baseline model, I need to develop a better model, fine-tune its hyperparameters so you can get much better results. And when you are happy with the results, you can just document your results. And after that, you will deploy your model, right? Maybe it's a web app, right? So you will just, the back end will be my model, and it will provide decisions to the end users in the front end. So this is very important to follow this development workflow. How to appropriately define how can we define our problem? So we need to answer some questions to define our research problem. So what is the main objective of my problem? What are we trying to predict? What is the prediction? What was the target feature which we try to predict, for example? So what are the target features? What is the input data, input features? Is it available? What kind of problem are we facing? Is it binary classification? Is it clustering? Is it regression? Because based on this, we will select the model which is appropriate for my data set or my problem. Can our outputs to be predicted given the inputs? Is there any kind of mapping between inputs and the outputs? Because in fact, I can collect any kind of data which is not connected with the outputs, with the target feature. So in this case, there is no connection, right? How can we make this connection between inputs and outputs? If there is no connection, there is no physical connection between both of them, right? So you need to ensure that the target features can explain. No, in fact, the target feature can explain, can connect, can map the output, the target feature. There is connection between inputs and outputs. Is the available data sufficiently informative to learn the relationship between the inputs and the outputs? Do you have enough data points? Because if you don't have enough data points, I mean, you cannot go for black box model. I mean, machine learning models, we call it black box model. And this black box model, it requires a huge amount of data to train it. So if you don't have enough data, don't go for black box models. Don't go for machine learning. There are other solutions which can be used. So you need either solve the data scarcity. You don't have enough data. So try to find more data. Try to use some tools to increase the size of the data, or find another solution. Don't go for machine learning. There are many other ways, in fact, which does not, and it will perform the same. So I can go for a white box model, not a black box model. This white box models, it could be fuzzy logic system. It could be expert, this rule-based system, or case-based reasoning, for example. So it's something which is based on human experience, not based on data. Because in machine learning, we learn from data. If you don't have data, don't build models. Don't waste your time. If you don't have data, try to find another solution. There are other set of models. We call it white box. And this white box models, it's based on learning rules. We call it rule-based learning, for example, or rule-based systems, or case-based reasoning, for example. Right? So data collection, you need to start by data collection. Data collection is the process of gathering or measuring information on the target variables in an established system to enable one to answer questions. Maybe you need to collect your data, right? Data sources, it could be sensors, surveys, interviews, books, images, magazines. So try to collect the data from many different sources, right? Don't ignore any source of data. We can use sensor fusion or data fusion, for example, right? If you are collecting data from different sources, we can try to combine it together to enhance our performance. There is also something called yeah, I forgot about it, in fact. So we can use different data sources for building our systems. It's called yeah, I forgot about it, in fact. So where we can build the systems which can consume images and data, different types of sensory information at the same time. The more and the better data that we get, the better our model will perform. It's very important to collect a large amount of data and high quality data also. This is very, very important if you want to build a good model. After doing this, you need to choose a measure of success or evaluation metrics, because I need to evaluate my model. I will train a model, but I don't know if this model will perform well or not. So in this case, we need to select a measure of success or some evaluation metrics. So there is a saying which is famous: if you cannot measure it, you cannot improve it. If you cannot measure the performance of your model, you will not be able to enhance the performance of your model, right? So what is considered a success? It could be precision. I need to achieve high precision. It could be high accuracy, recall rate, maybe fairness, biasness. My model should not be biased, because I can build a model, for example, which select people for job, right? So I have a system, and this system will consume all CVs of people, and it will classify them, and it will rank them, right? You know, systems, I mean, in hiring process in many places, I mean, they are biased against maybe women, correct? Maybe they are biased against people from Middle East, right? They are biased against black people, correct? So are applying for a job. If your system is biased and you are providing your image, your pictures, your name, for example, so maybe the system is biased against the black people, so it will not select you, it will not rank you. Maybe regardless of your qualification, right? Because the system is biased. Why my system is biased? Because in fact, I trained my system with biased data. So because when we are building a system, we will collect the data, and we will get those, hiring, CVs and historical data, which in hiring a company, for example, they have lots of documents, and for this CV he is hired, for this CV he is not hired, and so on. So I will use those data to train my model. But those files, in fact, those data are biased. It's biased against the black people, and it's biased against people from Middle East, and so on, for example. So in this case, your system will be biased, and it will not provide fair evaluations of people with fair classification. We need to know how to measure it, right? If you can measure it, we will be able to minimize it, for example, right? In regression problems, maybe you need to select a cost function like mean squared error and loss function, loss value. It could be mean squared error, for example, when it is a regression problem. And if it is in classification problems, maybe you can focus on precision, recall, accuracy, F1 score, right? So when it is regression, we try to minimize mean squared error between actual and predicted. But when it is classification problems, maybe for each class, we need to calculate precision, accuracy, recall, and F1 score for each class. Right? Not for all, not overall, but we need to do this one for each class. If you have 10 classes, we need to get those numbers. So you can say, you can discover that this model is perfect with all classes except the class 7. It's not good for it. So in this case, we can find a solution. But if you will get overall precision, overall accuracy, overall recall, you will not be able to discover those small stuff. So when you are getting your classification report, there is very simple command in Python called the classification report. When you use this classification report, it will give you precision recall, precision accuracy recall, and F1 score for each individual class. It's very, very important. So you can discuss that, okay, this model, it's perfect for all classes except, for example, for class number 7 or class number 4. I mean, this model, it works well, but it's biased against black people. How can I discover it? I can discover it from those numbers, right? So in this case, we need to find a solution, because it will be bad, really, if I can use a system which is biased against some people, for example, right? The evaluation protocol, this is very important. The evaluation protocol, to measure the progress toward achieving your goal, we need to have an evaluation protocol. One of the famous evaluation protocol, it's called hold-out validation. And in this hold-out validation, we try to split the data into 3 parts or portions or containers: training set, testing set, and the validation set. So you need to divide your data into 1 part for training. In fact, in reality, it's 1 part of training, 1 part of testing. And from the training part, we need to divide it 1 more time to get part for validation, right? So because I need to validate my model during the training process to discover if the model is overfitting or not. Without validation, you cannot Without the validation set, in fact, you cannot discover that your model overfits or not. So validation set is very, very important. There is another, we will go into details, later on. K-fold validation. In K-fold cross validation, we split the data into K-folds or partitions. And for each K in the, for each small K, for example, we train the model with K-1. We train the model with K-1 partitions and evaluate it in partition number K. And we will repeat this process K times. And each time we will calculate average accuracy. Each time we will get an accuracy, and at the end we will calculate the average accuracy of your model. And after that, you will train a brand new model with the whole data, and you can just claim that, okay, the accuracy of this model, the average accuracy will be this accuracy, which we got. There is something called iterated K-fold cross validation also with shuffling, for example, and we use it when having very little data available. And we apply K-fold cross validation several times and shuffling the data each time before splitting it into K partitions. This iterated K-fold, when K-fold cross validation, we will split my data into K-folds, and we will train the model 5 times or K times, and each time we will get this accuracy, and at the end we will get an average accuracy. In iterated, in fact, you will repeat this K-fold cross validation several times with shuffling, right? So it makes sense. So I can repeat it maybe 10 times and using K equal 5. But if you didn't shuffle, you will get the same set. So there is no change, right? So there is no difference. So each iteration, in fact, you need to shuffle and split the data into K folds and cross validate your model, right? So in fact, the K-fold cross validation, it's very, very important. If you are writing a paper, for example, and if you didn't use K-fold cross validation, you will get this question: why didn't you use K-fold cross validation? You will be asked this question if your dataset is small. But if you have a very large dataset, no one will ask this question, because it will be clear that you selected hold-out validation. We use hold-out validation when we have large dataset. We use hold-out validation when we can afford having a test set, because the test set, it will not be used in training, right? Test set, we will hold it out for testing. So we will not use it for training. So usually people do this when they have very large data set. But if you have a small data set and you collected your data set in an experimental part in 1 year or something, and it's expensive really to get those data points. So imagine that you are collecting data points from a hospital, for example, and it's expensive because it's operations and it takes time and so on. And at the end, you have only 100 data points. You have only 100. So if you said, okay, I will go for hold-out validation and I will use 80 data points for training and 20 for testing, no, it's luxury, in fact, because you cannot afford using 20 for testing. I need to use the whole data set for training. If you want to use the whole data set for training, in this case, you need to go for K-fold cross validation or iterated K-fold cross validation, because we will use, in fact, as you can see here, we will use the whole data for training. We will use this K-fold cross validation to calculate an average accuracy, and after calculating this average accuracy, you will initialize the weights again, and you will train the model using the whole data, and you will not evaluate the model again because it has been evaluated already in K-fold cross validation. So we use this technique when we have small data sets and when we cannot afford hold-out validation. Yes, multimodal. Yes, thank you very much. Thank you very much, Raphael. So it's multimodality or multimodal when we are working with models which are dealing with different types of data. So I can work with images and I work with text data, different types of data at the same time. We call it multimodality or multimodal. In classification problems, both training and testing data should be representative of the data. We need to shuffle before splitting, and all classes should be equally represented in training and testing sets. It should be balanced. Did you hear about imbalanced data sets? So imagine that we are collecting data and we try to diagnose a kind of disease, for example, right? And this kind of disease is rare, in fact. So we collected 1,000 data points for 1,000 patients, for example, and we have only maybe 100. So in this case, if I will split the data into training and testing without ensuring that each class is represented, maybe in fact you will have a problem. Maybe you will train the model using the 100, and in the testing you will not have any data points in the testing set from this class. So it will be a problem. You will get misleading numbers. But also, if you will train the model using 100 data points from who got a disease and 900 who does not have the disease, your model, in fact, your model will be biased against, in fact, those sick people. It will not it will classify sick people as non-sick people, in fact, because this model has been trained with many normal people, right? So it will be very difficult for the model to classify sick people because the model has been trained using very small set of sick people. Balanced training might impact the final prediction, real data sets which is not balanced actually. Yes, of course. Yes. Can you explain, Sophia, please?
Yeah, what I'm trying to say is that, for example, if your actual data set is really biased, for example, if I try to give an example in a real industry problem, for example, churn prediction in telecom sector, for example, where customer might leave your company. So it's like 99%, like 0.9 and 0.001, right? 1% customer might leave and 99% customer, for example, stick to your company. So predicting this 1% is really a big problem. But if you balance your training set, and finally after when you predict it, it might create an impact on the final prediction because you are balancing your data set, but your actual data set is really biased. That's what I'm trying to say.
Yes, this is correct. So you mean that if we have, for example, 1 million customers and 1% will leave, we are expecting that 1% will leave, which will be 1% of 1 million. It's what? 100? No, it's 10,000, correct?
Yeah, exactly. Yes.
It's 10,000 customers. They will leave. We are expecting that those 10,000 will leave us. So we need to build our own data sets. So what will be the size of your data set which you want to use? We cannot use 1 million data points because only 10,000 they will leave, and the 99% they will stay with us. So in this case, should we train the model with 20,000, 10,000 who will leave, and the 10,000 who will stay with us?
Yeah, so if we create a training data set, for example, 10,000 customers who leave and then the 10,000 customers who don't leave. So it's a 50-50% balanced training set, right? So if we train the model and we test the model in a same balanced environment, that's fine. But when we score the model, it means that when we apply the model to predict churners from 1 million customers, right, then our model would likely to predict 50% are churners and 50% are non-churners. I mean, the model will be biased towards predicting more churners.
Yes.
That's
Yes,
what I'm
this is
trying to
correct.
say.
So how can we solve this problem?
So normally what we try to do that we usually scaled our predictions. For example, that what is the actual probability distribution of the churners, and we try to there are a number of methods. So one of the simplest method is that we try to normalize or kind of standardize our predicted score with the value of the actual percentage of churners, for example maybe 0.01 or something, to lower the predicted score actually.
Yeah, it would be
Yeah.
nice. Is it possible for you to make an example?
Yeah, I would create an example maybe next
Yes.
time.
So example with coding, please. So you can just present it, for example, next time or the week after next time.
Yeah, sure, definitely.
Okay, good. Thank you very much. Do you have a data set already?
I don't have it right now, but I can create it one. That's fine. Yeah.
Okay, we can test it with any benchmark data set, and we can make these conditions, right? And we can
Yeah.
see how it will impact the prediction.
Yeah, definitely.
Good.
Yes.
Yeah, thank you. Yes.
Thank you.
So in classification problems, both training and the testing set should be representative of the data shuffled before splitting, and that all classes are equally represented in the training and the test sets should be balanced. Don't shuffle if you are trying to use best to predict the future. So if you are working with a time series, you don't need to shuffle it, because shuffling a time series will destroy time coefficient here. Check if there are some duplicates and redundant data to avoid inaccurate learning. Because if you have some duplicates, maybe I have some examples which are in the training and in the testing at the same time, so it will give us misleading numbers. So it's very important to remove those duplicates or redundant data. Okay. So this is in fact it's a holdout validation, as you can see in this graph here. Okay. This one holdout validation where we divide the data into one part for training, but we need to shuffle it first. So and we will divide it. Maybe it's 80%, 20%. So 80% will be used for training, and maybe 20% will be used for testing. Correct. And again, we need to take part from this training set for validation. So this one, that part, maybe 10% or 15% will be used for validation. So one part will be used for testing, one part will be used for training, and the part from the training set will be used for validation. And as a validation set, in fact, it's the test set for the training set. So this one, it's hold-out validation. You can go for hold-out validation if you have enough data, if you have large amount of data. But on the other side, we can use a k-fold cross validation when you have less amount of data and you don't want to sacrifice a data set, a test set. So in this case, we will divide it into k partitions. Maybe you select k equals 3 here, for example. Of course, we'll shuffle first, and after that, he will divide it into 3 parts. So this is 3 containers. And after that, we will train for 2, test for the third, and we will repeat this process 3 times. And each time you will calculate the score, maybe accuracy score, for example. And after finishing this one, you will take the average of those. You add this one to this one, plus this one. You will take the average score, for example. This one will be average score. So now you have the average score of your model. So you can just claim that if I will have this model, maybe this model will have because for the fold one, for k equal 1, for example, maybe the validation score here is, maybe the accuracy here is 85%. Maybe for this one it was 90%. Maybe for this one it was maybe 95%, correct? So in this case, we will take the average. We will add the 3 values together and we will divide it by 3. So we will get the average score. So maybe the average score will be 90%. So we can say that, okay, this model will have a minimum accuracy or average accuracy of 90%. In fact, you can get also the average accuracy plus minus standard deviation. It will be nice. It will be more professional. So you can say that, okay, my score will be this average value plus minus standard deviation, for example. And after doing this, I will use the whole data again. I will reinitialize my model, and I will just use the whole data for training my model. And we don't need to do any tests again because we did the test already and we have an average accuracy. So because in this case, you can see that we used the whole data for training, right? We didn't sacrifice any data for testing. So k-fold cross validation is very important. Data pre-preparation, data pre-processing aims at making the raw data at hand more amenable to the neural network, would include vectorization, normalization, handling missing values, and feature cell extraction, for example. So if you have some categorical variables, you need to replace it with some numerical values, for example. And maybe you need to normalize your data, so all your data will be normalized. It ranges from 0 to 1, for example. It's smart. And the normalization is important because I mean, if you are working with a problem and you have some input features and the range of the input features are different, so it will be smart to try to normalize it. So you don't, when you normalize all inputs will have the same impact on the output, correct? So the neural network model will not give any preferences to any inputs, right? Because all inputs are within the normal range from 0 to 1, for example. And also, in fact, because of sometimes we are using some activation functions, and those activation functions, it will show those high values and low values. So if you, for example, if you are using sigmoid function, So this sigmoid function, it will squash all inputs from its range into a number between 0 and 1. So all large values will be converted, in fact, into 1. All large values. So imagine that you have an input which is income or company income, which is you classify companies, for example, and all incomes they earn maybe 10 million, 20 million, 100 million, billion, and so on, large numbers. So if you did it to normalize it, it will not classify it correctly, in fact. You will destroy this input feature because all those large numbers, it will be squashed into 1. If you are using sigmoid activation function, all those sigmoid activation function, it's like this one, this function. So we convert all those numbers into a number between 0 and 1, right? So this is the input, which is x, and this is the output, which is y of x or f of x. So it will convert. So even if this number is plus infinity, it will be converted into 1. If it is maybe 10 million, 20 million, 30 million, no difference. All those numbers will be converted into 1. So in this case, this input feature will not make sense for my classification problem because I destroyed it, in fact, because I'm using an activation function which squash all those large numbers and convert all those large numbers into 1. So all those large values will be converted into 1. So there will be no difference between a company which earned 10 million per year and 20 million per year and 100 million per year. No difference, right? Because all those numbers will be converted into 1. So it will be smart to normalize, because when we normalize, we are sure that all values are between 0 and 1. So in this case, 10 millions, it will be a number here, maybe 50 millions, it will be a number here, 100 millions, it will be a number here, 1 billion, it will be a number here, correct? So in this case, we will be able to convert those input features into something which makes sense to our classification problem. So normalization is very, very important. We have also standardization, and the standardization will try to standardize the data, input data, to have a mean value of 0 and the standard deviation equal 1, for example. We need to handle missing values. If you have some missing values, you need to you need to handle it, correct? Missing values, I need to replace it with a number, a value, maybe the average value of that column. Feature extraction. Sometimes we have features, a set of features, and I have some duplications or redundant features. I have a feature which is a function of some other features, so it will make no sense for us to use features which are linear combinations of other features. So we need to select the most important features, the most unique features which will help us to solve this problem. So we can use those feature extraction or feature engineering techniques. Dealing with missing values, we need to eliminate features with many missing values. If you have not eliminate, for example, if you have an input features but it has lots of missing values, right? For example, we need to classify people and they ask them to provide age, and they don't provide age. So I have a sample which consists of 1,000 and I have only 10% provided age. So in this case, age does not make sense, right? So in this case, I will just remove this feature fully. I don't need to keep age because it does not make sense. Without the risk of losing relevant information, you just eliminate the whole feature, imputing the missing values with estimates such as the mean value of the rest of the samples. You can also this imputing, data imputing, which means we will replace those missing values with the average value of the column, correct, for the rest of the samples. Data vectorization means we handling a categorical data, for example. So we need to convert those categorical values with an integer, for example, correct? So if you have an object, maybe animals, we try to iris data set. We have 3 classes, Setosa, Versicolor, Virginica. So we need to replace its category with a number. So our model can understand, because our model, it will calculate the loss function. I cannot calculate the loss function between a number and a text. So it's important to convert, to replace those categorical data with numerical values. Feature scaling, learning algorithms perform much better when dealing with features that are on the same scale. So we do normalization. It's called min-max scaling. So we try to rescale the features that was arranged between 0 and 1, for example, using min-max scaling. Standardization, we need to center the features at a mean of 0 and standard deviation of 1. So all features are normally distributed. We can also, there are some techniques which can be used for feature selection, like select k-based, for example. K, it's a variable. It's a number of features which you want to select. And it's based on some statistical functions which calculates the correlation between inputs and outputs or score, or there are lots of functions for doing this, like chi-square or many functions, in fact. Or we can use principal component analysis. Principal component analysis, it will try to compress the data into a set of features, right? It's principal component analysis, we can use it for data compression. So it will compress the data into a reduced set of features. Yes, this is correct. Hisham, yes, we can use ReLU. This is correct. Gradient vanishing problem, no scaling is needed in this case. Yes, I agree with you. If we can use ReLU, we don't need to scale, because ReLU, it will be able to deal with, with large positive values of inputs. So in this case, but negative values, you lose negative values, right? So if you use ReLU, it will convert all positive values into the same positive value, but it will convert all negative values into zeros. So if in your data sets, if you have some negative values, be careful when you are using ReLU, because all those negative values will disappear, right? Yes. Softmax also, it is used for calculating. In fact, it's not, it's avoid gradient vanishing gradient also, ReLU, it will help because it has better performance. But softmax, it is used for calculating the probability that this example belongs to this class, for example. So it is used in the output layer, and they call it softmax layer usually. So in multi-class classification problems, we use in the output layer, we use a softmax activation function, and the people call it softmax layer. So the layer, they call it softmax. So for example, if we are classifying M-nested dataset, we need to have softmax layer, because the softmax layer, it will calculate the probability of each character or each image belongs to which class, and the summation at the end will add to 1, the summation of those probabilities. So we have 10 outputs because we have 10 classes, so we should expect that the summation of those probabilities at the end, it will be 1. So it's normalize the probability, in fact. So we calculate the probability and we normalize it. Selecting meaningful features using a principal component analysis, using select key best, using autoencoder. Autoencoder, it will do the same as principal component analysis. Autoencoder, it's feed-forward neural network, which can be trained to compress data. We can use it for data compression, and we can use it for denoising. So in fact, autoencoder, it works in the same way as principal component analysis, but in principal component analysis, it's based on a statistical score, right? It calculates a score, and based on this score, it will convert, in fact, not a score, but it will calculate transformation matrix, and this transformation matrix will be used for converting input features into principal components. So we mentioned this also, that it's very, very important that you develop a benchmark or baseline model before going into the full model. So you need to select a model to train using X and Y. The goal is to achieve a model that can generalize, and which means it perform well on a never seen data. This is very important. So my goal, in fact, is to build a model which can generalize, which can perform well on new data, and therefore we divide data into one for training and one for testing. And the testing data, we keep it away from the training set, so we are sure that we will be able to test the model performance on unseen data. We need to split the data into maybe 3 sets: training, validation, and the test. In the training, we adjust weights. The learning process, in the training process, in fact, we adjust model weights or model parameters. We validate set is used as a test set for the training set. From the validation error and accuracy, we can discover overfitting, if your model is overfits or has intentions to overfit or tendency to overfit. We can discover it from the validation error and accuracy. So in fact, it is highly recommended during the training process to plot validation error and accuracy against training validation and accuracy, because from this curve, you will discover quickly, immediately, that your model will overfit. And if the training process is time consuming, maybe you are building a model which will take maybe 10 days for training. So it will be really annoying if your model will overfit after completing the training process, you discovered that your model overfits your data, and you need to repeat this process one more time. So it will be really annoying. To avoid this, you need to define a validation set, and from this validation set, you will calculate validation error and validation accuracy. And you can use a technique called early stopping. And this early stopping, it will look into the validation error and the accuracy. And when it sees that the validation error, it started to increase, it means that your model started to overfit your data. It started to just memorize the data. It cannot generalize. It will stop training the process. And in this case, you will avoid losing the time which has been used already for training your model. So the early stopping technique, it's a very important technique which we need to use, and it helps us to save time, in fact. But to use early stopping, you need to have a validation set. Without validation set, you will not be able to monitor the performance of your model in the training process. In testing, we measure the generalization power of your model, avoid overfitting, and maximize generalization. Test set is used to evaluate the final model. I mean, after finishing training, we use a test set to test the overall performance of your model. And the model will overfit the data when it has high model capacity or little data. If you have very small data set, of course, your model will overfit it. Overfitting means your model will memorize the data. It will not be able to generalize. It cannot create a good mapping, but it will try to learn noise in the data, and it will not be able to generalize, and it will not be able to predict on unseen data correctly, right? So the performance will be very good for the training process, but in the test set, the performance will be very bad because it has been trained to memorize the data. And if you have a data set which unseen before, it will not be able to classify it correctly. So you can discover that your model is overfitting by comparing the test accuracy and the training accuracy, for example. But it will be too late because maybe your model overfits. So you need to repeat the training process again, and maybe the training process will take time. So in this case, you can just use early stopping to stop the training process when the model starts to overfit. Overfitting and underfitting, the optimization is the process of adjusting the model to get the best performance possible on the training data during the learning process. Generalization is how well the model performs on unseen data, and the goal is to obtain the best generalization ability of your model, right? This is very important. To improve generalization, more data, we need to get more data, we need to add weights. There are some techniques. It's called weight regularization techniques, L1 and L2. Maybe you can use early stopping. Maybe you can use also model reduction or size reduction. So if your model is very complex, very large, when your model is very large, it has high capacity, and the chances to overfit will be very high. So in this case, you can try to reduce the model size to reduce model capacity. You can use a technique called the dropout, right? So there are many approaches, many techniques which can be used for improving generalization capability of your model and try to avoid overfitting. One of those is early stopping, and maybe model reduction, dropout, L1 and L2 regularization techniques, and so on. So there are many ways for doing this. And as you can see here in this graph, for example, this is some values, and we try to build a regression model, right? This is values over time. It could be income. It could be anyway in stock prices, for example, over time. So you have the data set, which looks like this one, and you try to build a model to predict it. So you can say that, okay, at that point, I try to predict this value, for example. I mean, okay, this one here, I try to predict this value. At that time, I should be able to get this value. This is okay. But if here, for example, at that time, I try to predict the value. So the value here, do you see? This is the actual value, and this is the predicted one. Huge difference between the actual one and the predicted one, which error, prediction error. So in this case, we can say that this model is underfitted. Underfitted model, it means the model is too simple. Too simple. I just need to select a more complex model to train the data, right? So the model is too simple and it's underfitting. So I need to increase model complexity a little bit. When you increase model complexity, what will happen? You will be able to model this trend, right? You will be able to get those numbers. So now the performance of this model is much better than the performance of this model. I can predict all points here with reasonable prediction error. So at that time, I can predict that, okay, now it's here. This is the actual value, but this is the predicted value. So the difference is very little. Here, this is the actual value, and this is the predicted value, little. Correct? At that point here also, maybe I can go here. Oh, this is the actual value, this is the predicted value. So it's okay. So this model is a good fit, right? If you will keep training your model, it will overfit your data. And as you can see here, the model overfit your data. So it can learn noise in the data, and it cannot generalize. So now if you give it a new point, maybe I will give it a new point, which is here, for example. So do you see? Predicted value equals the actual value. So prediction error here equals 0. Prediction error here equals 0 all time. So the summation of the prediction error across from I equal 1 to n, it's equal 0. So when you see that your model perform very, very well on the test set, you need to feel worried, right? We don't need to get this 0 prediction error, but we need to get a number here. When it's a number, it means it's a good fit. This model will be able to generalize if it will be subjected to new data. But in this case, in our model here, it will not be able to generalize because it overfitted my data. And how can we fix this one? We can fix it by early stopping. And early stopping, I will stop the model in this stage. Because in fact, this model, before overfitting, it was like this one. It was good fit before overfit. So we need to stop training at some point. If the model will overtrain, it will overfit your data. So we need to stop training at some point. If you don't stop it, it will go to this phase, right? So we can say that in the first 2-3 epoch, the model will underfit the data, and with time it will be a good fit. And if you will keep training the model, it will overfit your data. So we need to stop training at some point. How can we do this? Using early stopping. Correct? We need to use early stopping. Maybe also it will overfit directly. If the model will overfit directly, it means the model is too complex, it's too large. So in this case, you need to do some reduction of the model reduction. For example, I have a model and the model has 2 hidden layers. Just remove one and keep only one. Right? Maybe in the hidden layer you have 10 neurons. I will simplify it. I will just use 5. So just try to reduce model size. When you reduce the model size, model capacity will be less, and the model will take more time to learn the data. It will take more epochs to learn the data, right? So it will not overfit. It will just learn the data, not overfitting it. So in this case, we know the difference between underfitting, good fit, and overfit. You need to develop a model that does better than a baseline. After building your maybe baseline model, you need to improve and enhance model capacity, for example. So the goal here in this stage is to achieve statistical power, develop a small model that is capable of being a dumb random baseline. So just a model which just when you toss a coin, it will give you 50%, 50%. This is a basic model or baseline model, and after that you will try to fine-tune the model to achieve better accuracy. This is a good direction for building your models. 3 key choices to build your first working model. Choose a proper last layer activation that matches your problem. So if it is regression, if it is classification, what will be the activation function which you will use, for example? If it is classification, if it is binary classification, maybe when it is binary classification, I can use sigmoid. Because in sigmoid, I can get 0 and 1, right? If it is multi-class classification, in this case, I cannot use a sigmoid because sigmoid provided only 2 outputs. So in this case, maybe I can just use softmax layer. When it is regression, what kind of activation function and so on. Choose a proper loss function that matches the problem you are trying to solve. For example, optimize configuration. What optimizer will you use? What will its learning rate, and so on. So there are many optimizers, but all those optimizers are based on a stochastic gradient descent, for example, or gradient descent. So how you will select the optimizer and how you will configure the optimizer parameters and so on. Today, okay. Yes. So you can use, for example, in binary classification, I can use a sigmoid. If it is binary classification. When it is multi-class classifications, I can use softmax. When it's multi-label or multi-class, maybe I can use a sigmoid. When it's this is the loss function, I can use binary cross entropy, categorical cross entropy when we have more than 2 classes, for example. When it is a regression, maybe I will not use any activation function because it's linear. I need to predict a continuous scale, right? So in this case, I will not use any activation function. If it is regression to values between 0 and 1, I can use a sigmoid, no problem. I can use a sigmoid. So I will get all the scale from 0 to 1, correct? Or I cannot use any activation function at all because I just need to get the output as a continuous scale, right? So I just need to multiply inputs with weights and add bias. So y will be omega x plus b. Will be okay. And when y equal omega x plus b, in fact, this is a regression model. Correct? This is a regression model. So you can apply the output one more time to an sigmoid activation function, or you can just keep it as it is, right? When you don't use any activation function here, it means it's linear, in fact. So we assume that we have a linear activation function, which like this one. So all positive values will be converted into positive values. All negative values will be converted into negative values. So when we have none here, when we don't have an activation function, it's the same as assuming that we have an activation function, which is y of x equal x, correct? Like this. Okay, I guess we have 2 slides left. So, okay, so feature engineering for reading, it's just an example. Feature engineering for reading is the time on a clock. In fact, I found this one in one of the books. It was nice figure, in fact. So you have some raw data, which is a pixel grid. You have this raw data, right? You have this raw data, and I need to estimate time, right? This is raw data. In fact, if you are working with CNN model, so in this case, I can just use this image as an input to my CNN model, and it will be able to estimate time, right? I don't need to do anything for CNN. I will just use the raw data, which is a pixel grid. So I will feed my model with this image, and in this case, it will estimate the time that the time is 3 and 3:10, correct? And I will feed it with this one. It will estimate time, which is it's 9, 10, 10. Yeah, it's 10 o'clock, right? 10, maybe 10. It's 22 evening, correct? So it will be like this one. So in fact, if we are working with CNN model, which is convolutional neural network, I don't need to do anything. I will feed it with the raw data, and it will be able to estimate the time. But in this case, in fact, we need to collect a large amount of images to cover the whole spectrum, right? Because I need to estimate time, so I need to collect large amount of data, and those data will be labeled, and I will feed those data to my model. My model will consist of feature extraction and classification, so it will learn how to extract features from those images and use those features for classifying or for estimating time, correct? So it will be okay. But if you want to simplify, if you want to work with feed-forward neural network or multi-layer perceptron, in this case, I cannot feed it with this raw data because it will be very complex, right? It will be very, very complex because this model will deal with it as a pixel value. It will be very complex for my model. So in this case, maybe I can work with feature extraction, and I can try to find the location of the clock handles coordinates. I need to find those coordinates, and I feed it to my model. So if I can find those coordinates, so for the hour and the minutes, I need to get x and y, right? Coordinates. So each point is defined by 2 points, x and y, correct? So I will have x1, y1, and x2, y2. So in this case, my model will have only 4 inputs. And in this case, I will train my model to predict time using x1, y1, x2, y2. And also, in fact, if you want to make, maybe this is black box model, this is black box model, you can go to white box model using a simple formula. So if we can find the angle of this each handle, for example, θ1 and θ2, maybe I can find a formula for calculating time. If you can know θ1 and θ2, I can find a formula for calculating time based on this one. So for example, if θ1 equal 90 degree and θ2 equal 0, right? So what will be the time? So if θ1 equal 90 degree and if theta 2 equal 0, so what will be the time? It will be 12, right? So it will be like this one, correct? It will be yeah, no, sorry. If both are 90 degree, so in this case it will be 12, right? And so on. So I can find formula, I can find the equation which will estimate time as a function of theta 1 and the theta 2. So you have a model, and this model will approximate time based on the input. If the input is raw data like this one, you don't need to spend the time working with feature extraction, just to go for CNN. But if you will go for CNN, you need to collect large amount of data to train the model, because you need to train the feature extraction part and the classification part or regression part, so you need large amount of data. If you want to go for feed-forward neural network or multi-layer perceptron, it's also black box model, but it's much simpler than this one, right? But it does not have feature extraction. So if it does not have feature extraction, you need to do it by yourself. So you need to get maybe the coordinates of the clock handle and maybe the hour handle and the minutes handle to train your model. So you need to spend some time by yourself. You need to work by your hand to extract features. If you are able to extract maybe theta 1 and the theta 2, for example, for each handle, so in this case, it's easy to just make an equation. So maybe time equal something multiplied by theta 1 and something multiplied by theta 2. So it will be function of theta 1 and function of theta 2. So it could be something like this one. So the amount of work, it will be based on your choice. If you have enough data, go for CNN. If you don't have enough data, spend some time working with those feature extraction to make the model simple, and they provide those clock handles coordinates to your model, and your model will be able to estimate time. If you don't want to use any models at all, just try to find an equation which will be used for estimating the time as a function of theta 1 and theta 2, for example. I think now we are okay. We have one more slide for today. So this is a place for feature engineering. If you want to do some feature engineering, I have here a model. I need to build a model, and I need to feed it with data. So you can feed it with raw data, if it is CNN model, for example, and those data are coming from different sources, sensors, and so on. So you will collect your raw data, you will use your raw data for building your model, and your model will do some classifications or regressions. If you need to do some cleaning and transformation, it should be done here, and transformations and feature extraction. So you can get a subset of features from the raw data and feed the subset of data into features into your model to get insights into your data and make classifications and regression and so on. So the feature extraction technique or feature engineering technique will be located in that place. It's before the model and after the raw data, so it can do some feature extraction, transformations, and so on. So that part is very, very important. Bad features may require much more complicated model to achieve the same level of performance. It's very important to select features which are relevant to your problem. If you can use something which is irrelevant, it will make your model confused. It will make lots of complication to your model. So it's much better to focus on feature selection and try to select something which makes sense to your problem. What about reducing learning rate to avoid overfitting? In fact, it will not reduce overfitting. It will delay it, right? So if you just select, Ihtisham, your question is about reducing learning rate to avoid overfitting. It will not avoid overfitting when you reduce learning rate, right? It will delay it, right? Because this learning rate, it's a step size which we use to adjust weights. If you made it very, very small, it will just take more time to overfit, but it will overfit anyway. It will take more epochs, more iterations to learn. So it will take more time until it overfits, but it will overfit. So it will not avoid overfitting. Reducing the learning rate, it will not avoid overfitting, but it will delay it a little bit. So instead of getting overfitting at iteration number 20, it will come at iteration number 25, but it will overfit, right? So learning rate, it will not help you, in fact, to avoid overfitting. It will just reduce, it will take more time to learn, right? So it's not one of the factors which are used to avoid overfitting. To avoid overfitting, you need to use, first of all, you need to start with a baseline model, simple model, and after that you can fine-tune this model to achieve generalization, right? But you can use early stopping, you can use dropout, right? But not learning rate. Yes. Okay. So thank you very much for today. I guess we are at 12 now. So we will finish. We didn't use the second break. So we will finish here today and we will meet again next week at the same time. And in the meantime, please, if you have any questions, just contact me, send me your questions. And if you have any questions, then we can just answer it immediately if you want. And for, I mean, things which we have been talking about today, we will go back to it on some weeks. So we will spend more time on those specific topics. So we can start, but today it's just overview of the whole process. But later on, we will go deeply into each of these subtopics, and we will cover it with examples. So thank you very much for today, and please let me know if you have any questions.
Thank you so much.
Thank you. And we
Thank
will.
you.
Thank you very much.
Bye.
Thank you.
Thank you.
Thanks, bye.
Thanks.
Thank you.
Thanks very much.
Thank you so much.
Thank you. So see you all next week at the same time.
Yeah, see you.
Yeah, see you.